All right, kids. Little late, sorry, but more time for you guys to do whatever you guys do. But so today we're going to talk about angles and vectors and all that fun stuff. Now, I mentioned this earlier before, the whole idea of conventional and unconventional. And that a conventional vector is what I would perceive of as the right way of doing things. That when you have a conventional vector, such as 3 meters at, let's just go 180 degrees, that both are positive and that theta is greater than or equal to 0 and less than 360. That if it satisfies both the fact that it's all positive and that the angle is between 0 and 360, you're good to go. Now, an unconventional vector could be like negative 3 meters at 180 degrees, 3 meters at negative 180, and you could even have negative 3 meters at 180 degrees. And so the skill that you'll develop this week and be tested on over next weekend is switching back between conventional and unconventional, or at the very least switching unconventional to conventional. So when you do these vectors in a conventional way, hold on. Okay. I really need to turn off my phone when I'm doing this. Okay. The first thing you do is you rotate counterclockwise to the angle, and then move forward to the point. Now, the thing that I will use to demonstrate this is the handy dandy tool. The tool always starts, and you can use this on the test. It's physical science. I'm not picky. But make something like this. And so it always starts with the positive on the positive x-axis and the negative on the negative x-axis. And let's say we did a conventional 3 meters at 90 degrees. Well, what you would do is you would take your handy dandy tool and then rotate counterclockwise. That's what CCW means. Okay. And the other thing I'm happy about, we've got football back. So I've got vectors, I got football. Life's good. Now, I rotated counterclockwise 90 degrees and I move forward. So we do that, and that is 3 meters at 90 degrees. Now let's do 3 meters at 225 degrees. And so the 225 degrees, once again, you start here, and then you rotate to like this. You're both positive, so you're going in that direction. And then you do this. So you can see that there is a pattern. So this is that, and that is this. And in the scope of, I'm going to get you a copy of the old test so that you can see what's expected. But you'll have a list of graphs with vectors, with letters, and then I'll give you this and I'll say which is the one that looks like the vector that I've just given you. Now, for unconventional, let's do the simple one, 3 meters at negative 90. So if it's negative 90 rather than positive 90, the fact that it's a negative number means that you 90 degrees clockwise. So for this, you have your tool. You're going to rotate 90 degrees clockwise. And now you move 3 meters in that direction that you're pointed. And so you go like that. And one of the things that I'll do is I'll ask you, convert this into its conventional form. And 3 meters at negative 90 looks like a 270 degree angle. And so 3 meters at negative 90, I would draw it out first and then label it. So 3 meters at 270. And that would be the answer. So in the case of a negative angle, you just go clockwise by the magnitude of that angle. Next comes negative 3 meters at 90 degrees. And you get the axes all set up. Now, you start in the normal position like always. You rotate counterclockwise 90 degrees, and now you step backwards because that number is negative. So positive, forwards. Negative, backwards. And so you go 3 in the negative direction when the tool is at 90 degrees. So you go backwards. And so again, you end up with 270 degrees. And converting it into a conventional vector, you just look at it and go 3 meters at 270. The last one is the double negative. Let's do negative 3 meters at negative 90. So you start in the conventional setup, the angle is negative, so you're going to rotate clockwise 90 degrees. That value is negative, so you're going to go in this direction. And so you end up with this. And that looks like 3 meters at 90 degrees. Okay. And so that goes over the 3 snarky type vectors. Now, there is a 4th kind. One where you have 3 meters at 410 degrees, where the angle is greater than 360. And to get rid of that, what you do is you subtract 360 degrees until you get an angle that is between 0 and 360. So the 3 meters at 410 is actually 3 meters at 50. And then if you were to draw it, like with the test, you're not actually going to be drawing these vectors. You're going to be just identifying them on a page. And so that's about 50 degrees. Probably not, but. So there are the 4 types of snarky vectors. I'll have a homework set up. I promise you I'll do it tonight and get it to you guys. And then we'll kind of go over the test Tuesday, and then do more test review online on Thursday, and then we'll do the take-home exam. All right, so those are snarky or unconventional to conventional. Now, there are, in our situation, there's another type of vector game that we'll be playing, and that is converting polar vectors from absolute angles back and forth with reference angles. So that is the angle symbol. Now, I'm going to be drawing what I call the vector butterfly. And it represents the 4 possible vectors because there are 4 possible quadrants. So the 4th quadrant is down and to the right. The 2nd quadrant is up and to the left. The 1st quadrant is up and to the right. And then the 3rd quadrant is down and to the left. Now, In the last lecture that I did, I kind of set this stuff up. When's it positive? When's it negative? What are the ranges? And really, the only thing that we need at the moment is to know that theta is greater than 0 and less than 90 for a first, that theta is greater than 90 and less than 180. Here, theta is greater than 180, but less than 270. And then over here on the right, you have theta greater than 270, but less than 360. All right, now, the absolute angle always starts on the positive axis and goes counterclockwise. So for each of these, and I need, be right back. Template, got my protractor. This is the protractor that you can get at Dollar Tree for $1 or at Walmart. And I'm going to mark the reference angle, or the absolutes. There's for the first one. This is for the second. Oops. Let's do that again. And use blue this time. Okay. And then third quadrant, we use this, and then for the fourth, we're gonna use, let's do this. This. Okay, and so as you can see, in all four cases, these absolute angles that I measured all go counterclockwise. They all start from the positive x-axis. And they go like this. Now, the reference angles always starts on the positive or negative x-axis. And in this particular case, even when the vector goes clockwise or counterclockwise or whatever, that the theta r magnitude is always greater than 0 but less than 90. That has to be true. And so absolute angles you denote by theta A, and reference angles are done by theta R. And I will mark the reference angles. Let's see. Now, well, this one is easy. The reference angle for the first quadrant, actually, I'm just going to sketch it. For the first quadrant is the same as your theta A. Theta A is equal to theta R. They're the same. It's the easiest one. If it's a second quadrant, for the second quadrant, that is your reference angle. And this is your absolute. For your third quadrant, it's like this. And then for your fourth, it's this. So one of the things that you notice about in every single case, that theta R either goes up or down from either the positive or x-axis or negative x-axis. So let's look at these relationships. Theta A is equal to theta R. So if I have 3 meters at 45 degrees, my theta A is 45, and my theta R is also 45. They're the same. 3 meters at 20 degrees, reference and absolute are both 20 degrees. For the second, what can you tell? The theta A is here, the theta R is there, so that theta A plus theta R is equal to 180. That they, when summed up, you're going to get 180 degrees. So if my theta A was 135, my theta R is 130. My theta R is 180 minus theta A. Or 45 degrees. In the third quadrant, theta R plus 180 is equal to absolute. So this is my theta A. 180 degrees is the half circle, and then you add on theta R, and then you get 180. So if my absolute was 250, my reference is 180, 250 minus 180. or 70 degrees. And then for the last one, the theta A and theta R must add up to be 360, because it makes a full circle. So if your theta A was 300, your theta R is 360 minus 300, or 60 degrees. And so those are some those are some conversions that you can make for each of these. If you remember that in each quadrant has its own set of rules to convert one to another. So remember those 4 rules. You'll have the notes on the test. I'm not worried about this. But this shows you how to do that kind of thing. So you have to identify what quadrant you're in. Now, there's another type of conversion, and we'll be going over that right now. And that is, there is the absolute format, and the quadrant format. The absolute format is like 3 meters at 270 degrees, or 2 meters at 130 degrees. And just to make things easier, I'm going to change that 270 to 210, since it's just right there. So the quadrant format has a magnitude, and then you do an at symbol, and then instead of theta A, you use theta R, and then you write down the quadrant number. So for something like 3 meters at 210, the 3 stays the same. A 210 degree angle is a third quadrant vector, so you write down a Roman numeral 3. And then 210 degrees is like that. So your theta R, using the other page, is 210 minus 180. Or 30. So 3 meters at 30 degrees, third quadrant, is the same as 3 meters at 210. And we'll do more of this on Tuesday. A lot more of this on Tuesday. 2 meters at 130. Well, 130 is it's like a second quadrant. So if that's 130, the 2 meters at 130 becomes 2 meters at second quadrant. Now, what's the reference angle? If that's 130, then that has to be 50. And so you get that. And that is your that's your conversion from absolute format to quadrant format. And you'll get a few more of those on the test. So the last thing that I want to talk about today is those instant conversion vectors, we may have talked about it on Tuesday, but it never hurts to repeat this again. So what I've done is I've taken vectors and stripped out most of the math, except for the parts where you add, subtract, do some simple multiplication and division. But even for vectors, it's all just addition, subtraction. And there are 4 vectors that are instant conversion vectors. They are vectors where you don't have to think other than identifying that they are an instant conversion vector. And those are, I'm offsetting it just so that we can see it. The more I think about it, the more that I think we've covered this on Tuesday, but it never hurts. So all of these are aligned with one particular axis. Here, the degree is 0, 90, 180, and 270. They are all multiples of 90 degrees. And in the test, you will be asked to convert a few of the simple ones like this. Now, some of my my algebra and trig-based students would try to do the math on this, and it's completely unnecessary. You guys can't do the math on this, and so you guys won't have a problem of just looking at it and going, boom, that's what this is supposed to do. 3 meters at 0 is positive 3 x hat. That 3 meters at 0 degrees is the same as positive 3 x hat. The 3 meters at 90 degrees is 3 y hat. Now, if I was being picky, put the units on the outside. But your tests are going to be all multiple choice. So now this one is negative 3 x hat meters. And then the last one is negative 3 y hat meters. And then those are all drawn out. So 0, 90, 180, and 270. That those are the ones that you can instantly convert and are basically just free points if you can identify it correctly. And so that is that's a really quick introduction on this stuff. When you get the homework, I have to figure out when to make it due. But most likely it'll be due on Thursday so that I could release a solution set for that homework on Friday morning. And then you guys will be ready for the test. So, and that is, as far as I know, that's all the new material that we're going to be going over. I know there was mention of Newton's laws, but we're not going to cover that until test 2 material, because I think we've got enough on our plate to work with this. All right, that's it. That's all I got, and I will see you on Tuesday. Have a great weekend.